And welcome. This is the second part of the video series where I make the Sudoku solver. And in the first part, I just made it barely work. Basically, I was just aiming for the functionality. And let me demonstrate what it is that it's doing. But it's basically figuring out every possibility for empty cells, and then it's just kind of going row by row and filling those in. And then if it runs out of options, then it's gonna sort of go back to where it came from and trying out different possibilities. So definitely watch that previous video if you're unfamiliar with backtracking. But I want to see something what's going on with the code. I wanted to so what this is whenever this backtracking is called, we just increment this counter. And this is going to be kind of a proxy for performance, because right now we're solving it fairly quickly. But if we can get this count, it'll tell us like if we are doing something stupid, or if we are like not limiting our search space very well. So after I call backtracking, if I just say I want to show, and I'm going to run my code, and it is 7,000. So it is fairly large. I mean, it's quick enough, but I think as I'm working on this code base, this number can definitely go down. And several strategies on like how it can go down. We might change the order in which we are doing these cells. So that way, if this one has like 3 possibilities, but maybe this cell has only 2 possibilities, then we're gonna bifurcate on this cell first, thus removing possibilities later on. So I just wanted to have this number as like a proxy for my performance. And I don't like this code particularly well the way it's written right now. From what is happening is I kind of have this repetition. Everything is repeated 3 times. Row, column, box, row, column, box, and then row, column, box. Now you can think about if I start adding more rules for thermo sudoku and killer and various other kinds of, this is just gonna get really messy, right? Like this function is just gonna keep expanding, it's gonna keep getting bigger and bigger and bigger. It'll be a lot of copy paste. So ideally, right now, I don't want to implement anything else until I fix, until I don't want to implement any new functionality until I fix the little bit of structure, like make this slightly better architected. So then adding more types of constraints, it's going to be easier, right? There's going to be better separation of concerns. And the way I'm thinking about it is that basically, ideally, I want to have every row, every column, and every box have like a one object, right? It's going to be some kind of constraint object that's gonna, whose goal is going to be to track what it is that we've replaced, what are the remaining options that we still haven't placed, and so on. And for now, we just have one type of constraint. So I'm imagining, let's say that there's going to be this uniqueness constraint. And this is, let's say, for column 1. So what this one is responsible is to keep track of the uniqueness. And let's create a couple of more these uniqueness constraints. Let's say I'll have, again, uniqueness, but this will be row 2, just an example. And then again, we're going to have something else, box 0. And let's consider the world from the perspective of each constraint, right? Like what the world is going to be asking me is, well, first of all, the world is going to tell me like, hey, you have this cell attached to you, right? So if I create, let's say, some kind of a constraint, a uniqueness constraint that represents the first column, or sorry, the row 0, then I'm gonna have cells that are getting attached to me, right? I get 9 attachments to me. So I can imagine that there's gonna be some kind of cell 0, 0. And that one, well, that one actually should be attached to box 0. And then I can have another cell, let's say cell 2, 1, as an example. That one will be attached to these 2 constraints. And so what this means is row 2. So row 2, cell 1 is this number 9. Well, it's getting attached to its corresponding column, row, and box constraint. Okay, so every constraint should have a function that says attach a cell to you. Great. What else? Well, each cell can set the value or unset the value, right? And this will be done either by the initial board, like we'll be given some initial board which will have to set those values, or our solver, as it is trying out all these different possibilities, then our solver is going to say set this cell to some value. And then basically our uniqueness constraint should get that signal passed to it that says like, hey, I'm the cell and I just got assigned a value, so you should probably know about it. So how is that relevant to a uniqueness constraint? Well, if it has a cell that has been assigned a value, right, then the uniqueness constraint should keep track of that assignment, because it should know that, let's say, a value 2 is no longer available to be given out to any other cell that is attached to the uniqueness constraint. And similarly, if we kind of go in the different direction, we can ask a uniqueness constraint or any kind of constraint. We can ask like what it is that you think are the options for this cell according to you, right? So so let's say if a uniqueness constraint has this bag of numbers, and currently there's like 1, 2, and 4 are already assigned to the cells that are attached to this uniqueness constraint, then when we get asked this question, like what other options are there, it should be able to answer 3, 5, 6, etc. And then ideally, when these options change, right, then we might notify a cell, right? We might say like, hey, by the way, your restrictions have changed, right? So now cell could have a multiple constraints that are attached to it, and in fact, every cell will have multiple constraints attached to it. The cell is getting these different signals. Like this one is going to tell him like, hey, you are restricted to 3, 5, and 6, but this one will tell you like you're restricted to 1, 2, and 3. So if those are the only two constraints, then cell can decide, well, I can only be 3. So with this kind of structure, we're able to reach the answers more quickly, and basically these ones are going to be keeping track of this sort of stuff. So let me see, right? I guess let's just start coding, and then we're going to be adding more complexity into it. But I just want to create like a class that's going to be representing a single cell. I'm going to create a uniqueness constraint, and then I'm going to like attach those to themselves. So let's, all right, probably this code is going to need to be deleted later on, because we're kind of re-implementing it in a better way. But let's say I'm going to have a cell. I'm just going to have a constructor, and I'm just going to have a value that will be null. So null means I'm not assigned. Right, we're doing this properly. Last time we were doing it with zeros. Now let's do it with null. That seems more appropriate. And this cell needs to just know what constraints do I have attached to me. So I can just say constraints is going to be an array, and I'm going to say add. I'm going to add a method. I'm going to add a method for attaching a new constraint to this cell, and it's for now. Let's just do constraint. Now, in this uniqueness constraint is basically where I want to implement a logic of like actually limiting things, right? This will keep track of a single row or single column, and it's gonna make sure that it cannot like 2 digits cannot appear multiple times, but this is kind of the bread and the butter of my solver, right? Because eventually I'm gonna have a exact sum constraint that says the sum of the values within these cells need to be a certain value, right? So that will be like killer constraint or little killer, right? And then again, I can have another type where I have a thermo constraint that says, well, now in a particular order, it has to be increasing. So ideally, these should be like my first-class citizens. Like I need to treat these constraints in the best possible manner, because I'm going to be adding a lot of those in the future. So let's say that I'm going to be tracking of which ones are available. Which ones are available? And for that, I can consider making a function bag all. It's supposed to return a bag that has all the items inside it. And if you remember what we were doing last time, I had these numbers, right, that were holding the set of digits that are placed inside this bag. So if I have like 0, 1, 0, 1, 0, 0, 0. That means there's like two items inside this bag. And then I can use or and, different kinds of operations in order to put a new item or take the item out. But if I just want to have a bag that has all the items, then what I can do is I can start with all zeros. Right? I can have a bag that just has nothing inside. That's just regular 0. And then if I do negation, it's going to turn into all ones. So it'll turn into a bag that basically has everything. So what this means is I'm just going to invert the value 0. And that'll be some strange number, but I don't care what the number it is exactly, as long as it has the right bits set. And we used inversion in removal previously. Basically, we would take just 1 and then shift that 1 in a desired position. And then inversion is going to turn that 1 into a 0 while turning everything else into 1. And this was useful in order so that we can remove item from the bag. So our uniqueness constraint is going to start with just bag all. Everything is possible. And it should have a list of cells. Easy peasy. Because we're going to be doing this propagation where once the value is set, then that needs to be propagated to constraint, but then constraint could propagate that even further to individual cells or to other constraints. I guess for now, just to individual cells. So we need a like attach cell to me. It's just going to take cell and okay. Now, what can we do with a cell and what can we do with the constraint? Well, one thing is for cell, we can set the value and unset the value. Easy enough. Let's say I'll just say set value. Oh yeah, so the reason why I use the name underscore attach self is I guess I'm just considering this to be like a private. It's going to be a function that should not be called externally, but should only be called within the cell or other constraints. So it's, I'm just kind of making it into like a little more restricted method. And the reason why I wanted to do that is basically when we add a constraint to the cell, we should also tell this constraint like, hey, by the way, there's a cell that's looking at you. So we can do that. We can do that straight away. We can say constraint attach cell this. So we kind of make a connection in both ways. Now we get our set value method. Now if you compare this set value with what we had previously, like sudoku add, right? That one was taking like row, column, and value. And that's basically because this didn't have a context, right? Whereas now every cell is only for a one particular cell in our grid. So we can kind of be more direct and just say, hey, I'm setting a value, and the cell either should care or shouldn't care exactly which one it is, because every cell in the grid essentially behaves the same way. So after I set the value, right, then I can say, okay, well, I'm setting the value, so that means I'm gonna set my property to be value, right? Next, what I can do is I can notify the constraint, like say, hey, by the way, my value has been set. I don't know if you care about it, but I just wanted to let you know about that. So we're gonna go, we can say let C of constraints so I'm passing in this because I'm kind of telling to the constraint like, hey, like you should know like which cell am I setting, right? I will like fix this design decision later on. I don't like that I have to like pass in this to the uniqueness constraint, but for now I will just like, it kind of makes sense that when you're setting a cell, you want to know, you want to tell the constraint like, out of your many cells that are attached to you, by the way, this is the one that got its value set. Okay. And we can do the same for unset value. Now I'm passing in the value that was unset. That is kind of similar to my to what I had previously here when I was doing sudoku remove, and I don't think it's a big concern. We just have to make sure that when we are unsetting the value, that we are actually unsetting the value that was on the cell. I can also do. I'll just add assertion. That's okay. Now my uniqueness constraint now has two new methods: notify value set and notify value unset. So when we get a notification that value was set on a particular cell, well, we should remove that as our available option, right? If somebody sets 2, we want to remove it from our bag. So we can say bag remove value. And when value is unset, we can put it back. So that makes sense, mostly. Yeah, these two things are all right. Let's do actual connections now. So I'm just going to do it in, let's say, I'm going to call it a name. So far, I lack good names for these things. But I don't worry too much about, because I think once we add more complexity, we'll be kind of like forced to do things properly, right? When things become complicated, then I'm gonna refactor, as I'm doing now. I'm doing some refactoring. Okay. So I need to make, let's say, row constraints. Right. To keep it simple, just focus on new constraints. It's gonna be an array, and I can say var I am doing some repetitions again. I realize that, but at least this is kind of repetition during creation. I think eventually our solver just um, should just receive like a template, like this is your puzzle, right? And then based on that puzzle, it will do this construction. So I think this repetition will be eliminated kind of later on. But for now, it's just a necessary evil. Um, and I want to now do these connections. Uh, what about cells? Well, actually, I like that these cells are. I like that these ones are just like regular arrays. Now my cells would actually have to be two-dimensional arrays. So actually, I prefer to make it into one dimension. Um, so what I'm going to do is I'm going to say cells are going to be 81. So I'll just allocate them all on a flat array rather than 2 by 2 array. Um, and this is a formula that I'm using to map a row and a column to a cell index. And it's not difficult to kind of see how this formula works. But for row 0, it's just going to be from 0 to 8, right? It's going to be just directly mapped. And then when row becomes 1, then we're going to take this column that goes from 0 to 8, and we add 9 to it. So we just kind of like shift it into the next position. So then what we end up with is this will be like 0, 1, 2, 3, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and so on. They're just laid out this way. So we're creating this cell, and now every cell needs to have attachments to appropriate constraints. I guess I'll just call it cell. And I made this function get box number last time, but it's essentially doing a math that's going to take row and column, and it's going to turn it into a box number. And box numbers essentially, again, they always start from 0. Basically, this is box 0, this is box 1, 2, 3, 4, 5. 6, 7, 8, and take a look and just convince yourself that this formula does the right thing. Right. So now I have all these attachments, right? Let's think about what else am I missing. All these rows are constructed. All these. I'm adding these constraints, and my phone is doing something. All right. Now, what happens when I set the value? Okay. Okay. I think the next missing thing is going to be to just ask the cell, like, hey, what options do you have available for you? Right? If the cell is not set, then it should be able to figure out what are the remaining options that are available for myself. I think that is the last sort of missing piece of the puzzle. Um, get available options. Sorry, my phone is buzzing. And I'm gonna start. So let's think about it. How does the cell know what are its available options? Well, the cell, like this one, is attached to a constraint, right? And every constraint can tell what are my limitations. So if this constraint is limited again to like 1, 2, 4 for this cell, and this one is limited to like 2, 4, 7, then what we're doing is we're just doing an AND operation, right? We're doing like a set intersection. Whatever was available here, whatever was available there, we intersect it. And I think for this purpose, we're gonna have to be able to take two bags and just intersect them. So let me discuss the bag intersection logic. So I'm gonna go back to my trusted bag code. I discussed it a little bit earlier. I have these 4 methods so far, right? Adding, removing, and then I will need a function bag intersect, or in both. Well, yeah. And if you've been following the logic so far, I'm gonna still go through it just in case if this bag logic is kind of unclear. But bags will have let's say one of them is gonna, I don't know, just have some digits 0, 1, 0, 0, 1, 0. So this one kind of has 3 items inside it. And let's say we have another bag that's going to be 1, 1, 0, 0, 0, 1, 0. And what are the intersections here? Like those would be only items that appear in both. So the way we do that in computers is similarly what I explained before, is we use AND operation. And then basically 0, we're gonna have a lot of zeros in the end. But essentially only 2 items were present in both, while the other ones were not. So that kind of makes sense from the perspective of what I talked about here. If this uniqueness constraint says that my availability is 1, 2, and 4, and this one says 2, 4, and 7, when we do the intersect, when we perform this AND operation on those available bits, we're going to get that this cell then can only be 1 or 2. Perfect. All right, so now I'm coming back to the logic of the cell. And get available option is supposed to return what are the available options for me. So I'm going to start by assuming that everything is available to me, right? And if this cell didn't have any anything attached to it, any constraint, then it can be anything from 1 to 9. So in which case, yeah, we can just return, we can return all of it. Right? But if it does have constraints, we should go over those constraints and perform this set intersection in order to narrow down the possible options. Let's see. All right, I will make a method that will be okay. So the reason why I am so I'm a little bit suspicious of this approach, and I think we're gonna have to fix this later. But basically, the uniqueness constraint has this available option property. Well, okay, I know what is the right interface. I can say get available for cell. So I'm asking my constraint for this particular cell, what are the available options? Well, the uniqueness constraint doesn't discriminate between cells. So we're just gonna ignore the cell passed in, and we're just gonna say it is this available. But you can imagine in sudoku, availability for each cell is gonna differ, right? Because the numbers in the sudoku has to increment within a constraint. And therefore, it varies between cells. But here, for every cell, it's going to be the same. So I'm going to be calling the constraint C, like for me, for myself, right? This refers to the current cell. Give me all the options for my current cell. So now the next step is I'm going to add all of these values that are already in my board. I'm just gonna like set those values because they're gonna be fixed. They're not gonna change. So I can do that, and I can say so I'm iterating again over all the rows or all the columns and then computing the index of the cell in this cells array, which is just going to be I. And I can say if board of row column is greater than 0, then cell of I that should be good. Now I want to see rather than rushing into solution, I kind of want to test what I've done so far, whether it is working or not. So I'm going to say like cell in my board, it should be 0, 1, 2. I want to see what are the options for this one. Ideally, it should be 1, 2, 4. But let us see. Console.log. cells of 2 get available options. And this one is gonna show a weird number, right? Because it's like a combination of things. So I'm gonna make a helper method that's just going to like just use for debugging. That's gonna like expand that number into something that's like visible. So I'm gonna call it show options for bag. So I'm going over all the numbers, all the possibilities, and I'm calling this bag check if it exists, and if it does, I'm gonna like just put that into a string. And now I should be able to see what is in my... All right, time to delete some code. I don't need this. This is all re-implemented. All right, showboard needs to be fixed. I will fix that later. This is all done. And backtracking needs to be fixed. And this is already done. So I will comment out the parts that I need to fix later on. So now let's see what we have so far. It is 1 and 2, which is incorrect. Because it should be 1, 2, and 4. I don't see why 4 is restricted over here. So let me check each individual row, cell, and row, column, box, and cell. So I'm going to do row. It should be row constraints of 0. Get available for cell. Then my column is going to be 2, and my box is going to be 0. Box, column. And basically I'm trying to debug this one. So I hope that makes sense. All right, so row is more restricted than it should be, while columns are unrestricted and box is unrestricted. So that is wrong as well. Let me see what I did wrong here. Row, column, cell. Right. Let me give a name. This should help with some debugging. Name. When I'm calling these, I'm gonna be calling it R. when I'm constructing cell, that should have a name too. I did not want to call it C. I just want to name it differently so that it's different from row, column, and the box. And I'm not sure if this even makes sense. Row, column, box. Okay. Let me check connections. Row, column, set value, row. Okay. Let me check connections of like a particular cell. So I'm gonna add something like debug a cell. Straight row, row, row. Oh, okay. Yes, I had a similar issue during my last episode. Damn it. All right, perfect. Now it's 1, 2, 4. At least we got some debugging utilities in case we need to do that in the future. Let me try 1, 1, which is 8, 9, it's 9 plus 1. 2, 4, 7. So 2, 4, 7. I think that makes sense. Right. This is all looking good. Let's try this one just for funsies. This is 8. 2, 4, 8. Perfect. That is all correct. How do we show the board? Well, now it's a little bit tricky, right? Because we're going to So our row, all right, so our values are written inside this cell under value. So we're gonna have to go like row by row and then access the right piece of this cells array. And I think I can do that. I can say this dot cells dot slice from row times 9 until row times 9 plus 9, and then I'm going to map it into cell dot value, or it'll be a space, and then I'm going to join that with spaces. Oh, that doesn't work. Okay, perfect. We are showing the board, and again, this is just gonna like select the right subset of the array and then convert it into either dot or the value, and then just show that in a single line. Awesome. And the remaining part is to do this recursion. So what is different now? Well, we still have this all works correctly. Get next cell, backtracking. This works correctly. Okay, so sudoku can be placed. So we only need to change these three operations. We're just implementing them in a different way. And what I need is just to resolve. Cell is going to be cells of row times 9 plus 1. And then I can say my options are going to be cell.get available options. I think that should work. Yes, that's giving me all the available options. Oh yeah, I can do that outside. And actually this check needs to change as well, which means I can take this out. So now what I'm saying here is cell.value is not equal to null. What does this mean? The purpose of this check is to see if there's already a value set in a particular place. We used to just look at the board array, but now we're keeping these values inside these cell wrappers. So we're just gonna reach inside the cell and see if the value is not null. If it's not null, then we can skip this cell because it only has one option and it's already used up. Perfect. And we're getting available options, and now we want to check if this number is an option. So we can do that through bag operation. Options are bags, and the number is the one that we're checking. And the next thing is we use sudoku add to indicate that we're setting a cell to a value. So now all we do is say set cell value, and this is after we return from the recursion. We gotta undo whatever we did, right? So undo is unset. So we just unset the value none. All right. So in theory, that should be working, but remains to be seen in practice. Wait, I'm confused. Oh. Okay, so it does work. I was confused by the second output because it was showing me something weird. But it doesn't matter. Wait, where's the board? Yeah, the board only gets used in this particular spot and nowhere else. All right. We're still getting the solution. I think our number of steps that we're taking to reach this solution hasn't changed, right? It is still 7079, and we are still doing the same number of operations. But hopefully this change in the way that we structure the software is gonna allow that in the future, we're gonna be able to make better decisions, right? We can, we have a more flexibility. So what does this flexibility give us? Well, think about it. The uniqueness constraint is essentially, it's all in here, right? We kind of have this logic very much isolated. This logic here kind of has to do with the shape of our puzzle, right? So I think this shape is gonna mostly remain fixed for the regular Sudoku rules, but for other rules, they're gonna just depend on the definition of the puzzle. So we kind of don't have a other choice but to keep this kind of code around, unfortunately. However, everything that's all the logic that's related to uniqueness constraint is now inside one class, which is something that I like. And every logic that's related to handling the cell is in one class, and so on. So like we haven't changed our algorithm, and what I'm thinking about next is if we could fix this get next cell logic, right? Because right now we're always going cell by cell, and I talked about this at the end of my last discussion. But let's say that that this cell has only 2 available options, but our worm could simply be trying out, like, whereas this one could have like 6. So ideally, if we can make a smarter choice about what cell we should go to next, then we will be able to reduce this recursion count, meaning that we'll be able to reach our answer more quickly. So those are the topics that are going to be subject of the next version of this video, and I will be adding more constraints and hopefully turning this into a better UI so that it's not just in the console, but it can be a nice web page, etc., etc. But thank you for watching, and let me know if you have any questions, and until next time, bye-bye.